How are you all doing this morning?
Pretty good.
Good. All righty. So today we are going to talk about sinusoids. And the reason that we're going to talk about sinusoids is because we are rapidly approaching the last really big topic for this class, which is called steady state sinusoidal analysis. So what steady state sinusoidal analysis is analyzing circuits who oscillate or are excited at a specific angular frequency. And the reason that we analyze these circuits is because that is how power, electrical power, is distributed by utilities in practically every industrialized nation in the world. Okay, so this is a really big concept here in electrical engineering. And for those of you who aren't going to be electrical engineers, this will be something that you'll be talking to or talking about with your electrical engineering co-employees, I guess, an awful lot. So this is really kind of learning the language to speak in an industrialized setting. So to preface all of that analysis, we need to understand how sinusoids behave, how to compare them, how to manipulate them, and all that kind of good stuff. So that's where we're going to start today. So I'd like to start by talking about the characteristics Dang it, this thing's about to give me that dumb error. Let me restart it. All right, I apologize. Characteristics of sinusoids. And some of, I believe we talked about previously when somebody asked a question about why we can't use a sine or cosine function as a guess value when we were solving our differential equations. So I'm going to apologize in advance for how crappy this is going to look. And just for the sake of argument, I'm going to say that we're looking at a sinusoidal voltage waveform. So something around this, okay? So any and every sinusoidal waveform is really described by three specific factors, okay? The first of which is its amplitude. And so I'm going to call that amplitude Vm. And that is the maximum value of the sinusoid measured from the horizontal axis, right? So it hits its peak value at Vm. And because a sinusoidal function has symmetry about the horizontal axis, its negative peak value is negative Vm. So there is additionally Vm distance between the horizontal axis and the negative peak. The distance between peaks is what's known as the period of the sinusoidal function, given by the letter t. We can also just as easily measure as the distance between the negative peaks. We could also look at what are called zero crossings and stuff like that. But when determining the period that way, you have to be very careful because you want to look at it when the signal crosses zero and is increasing to the next times the signal crosses zero and increasing. So until you're super comfortable with this, I would always consider the period to be the distance between or the negative peaks. The sine function v of t that I've drawn here could be written as Vm, so we have its magnitude, cosine omega t plus some phase angle that I'm going to call theta v. And I want to talk about all these different parts, all right? So as shown pictorially, Vm is the amplitude or maximum value of v of t. Omega is the angular frequency of v of t. And I'd like to talk about that a little bit more right now, okay? So what the period is, t, I'm going to do this as, I guess, kind of a subnote here. So t is the period of the sinusoid, and it represents the amount of time it takes for one cycle to complete. All right. You guys learned in Engineering 121, if I'm not mistaken, F is the linear frequency of a periodic function. I'm going to just say of the sinusoid in this case. And represents how many occur in 1 second. So there is a relationship here, then. T is exactly equal to 1 over f, because the period is the time it takes for a cycle to occur, and the linear frequency is the number of cycles that occur per second. So they have an inverse relationship. Well, our angular frequency is just the number of degrees or radians that occurs in 1 second. So omega is exactly equal to 2 pi f, because our sinusoid must undergo a change of 360 degrees or 2 pi radians over every cycle. And so from this then, we could write omega also as 2 pi over our period t. And that's going to be a very important quantity or relationship to remember a bit later on. So I'm going to put a box around that. It's going to be pretty dang important. All right. So we have talked about the amplitude. I think probably in reasonable understanding of what that means. We have talked about the angular frequency, omega, and I feel like you guys are all pretty okay with that as well. If you're not, by all means, stop me. The last thing that we have to talk about is this phase angle, theta v, and this is where things are going to get potentially a little bit confusing. So what the phase angle is representative of is the time shift in the waveform. Now, you may not have any earthly idea what I'm talking about right now, and that would be perfectly reasonable. But if I just had, let's say, 5 cosine 5t, at what time should I expect it to reach its peak value? 0. Okay. So that phase angle theta v just really shifted away from having the peak value occur, right? We expect the cosine of x to be its maximum value at t is equal to 0, or really omega t is equal to 0. And we expect it to be its minimum value when omega t is equal to 180 degrees. So I've drawn this guy intentionally, kind of shifted a little bit to the right to illustrate that there is some non-zero phase angle, okay? So theta v is what's called the phase angle of v of t and represents the shift in v of t along the horizontal axis. Positive phase angles (0 degrees is less than theta v is less than 180 degrees. Means that our waveform has been shifted to the left. Very important. By theta v over omega in time. And negative phase angles (0 degrees is greater than theta v is greater than negative 180 degrees. Means that our waveform has been shifted to the right. By theta v over omega in time. Now this probably seems counterintuitive. And what I mean by that is you would probably expect that a positive phase angle means that we should shift to the right, and a negative phase angle means that we should shift to the left. The reason why it's opposite is because what a positive phase angle means is that our sinusoid occur to the left of the vertical axis. If our phase angle is negative, that means that we are reaching our peak value later in time, which is represented by all the points to the right of the horizontal axis. Okay, so it seems counterintuitive, but there's a very, very specific reason that we're doing it that way. And it's because we, as humans, perceive time linearly, and we're used to seeing things that occur earlier in time on the left-hand side of our graphs and things that occur later in time on the right hand of our graphs. Omega is typically expressed, or not typically, it's always expressed in radians per second because it represents angular rotation. Our phase angle, theta v, is traditionally measured in degrees. So we're going to have a mixed unit argument inside of our cosine function that we are going to have to pay particular attention to whenever we're doing any sort of manipulation there. All right. So we can represent the exact same trigonometric function. So we can represent a sine as a cosine and a cosine as a sine using a few specific trig identities. So I'm going to list out several trig identities that we will wind up using in this class. Now I need to find my list so I don't make any dumb mistakes. There we go. So the first identity is that cosine of omega t is equal to the sine of omega t plus 90 degrees. So I'm going to attempt to draw another sinusoidal thing here. Let's say that this is v of t, this is t, and I'm going to start with cosine of 0 degrees. So, and actually, I'm going to change this ever so slightly. I'm going to call this guy, instead of t, omega t, so that it's representing an angle. All right. So when we have our cosine function, all normal and stuff like that, We know that it reaches its peak value at 0 degrees. It crosses the horizontal axis at 90 degrees. It reaches its negative peak value at 180 degrees. And then it reaches 0 again here at 270 degrees. And similarly, we could see if we go back the other way that it reaches 0 here at negative 90. So this is the exact same thing as a sinusoid, a sine function that has been shifted to the left by exactly 90 degrees, right? We would expect sine to at omega t is equal to 0 degrees to be 0, but instead it is occurring at omega t is equal to negative 90, right? So this cosine function here can be thought of as a sine function shifted to the left. I have sine omega t plus 90 degrees. Our second identity is then sine omega t is equal to cosine omega t minus 90 degrees. So that's just the inverse relationship of that first identity. Our third identity that we will make use of is negative cosine omega t is equal to cosine omega t plus or minus 180 degrees. Okay, so if I were to do a graph, I'll just do it on here. So this guy in red will represent negative cosine. Like so, we see that the peak value occurs whenever we shift our signal to the right by 180 degrees. But if I had drawn out my graph more, like so, it would also be representative of a shift to the left of 180 degrees, which is why we can say that it's plus or minus 180 degrees. And we can observe a similar identity for the sine function. So negative sine omega t is equal to sine omega t plus or minus 180 degrees. The next 5 identities that I'm going to list are going to be more mathematical manipulations of how to look at a single sine or cosine function as a sum of sine and cosine functions, which we will use thoroughly. So the first one that I'd like to introduce is sine of alpha plus beta will be equal to sine alpha cosine beta plus cosine alpha sine beta. Next, cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. I do have the sign correct here, so that should be a minus sign there in the middle of it. Number 7 would be sine alpha minus beta, which will be sine alpha cosine beta minus cosine alpha sine beta. And lastly, cosine alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta. So that's the last of those identities. Another useful identity, we won't use this one for probably around a week, but then it'll pop up a whole heck of a lot, is cosine alpha times cosine beta will be 1/2 cosine alpha plus beta. Excuse me, I'll do alpha minus beta first. Plus 1/2 cosine alpha plus beta. And there are technically other ones for multiplying sine of alpha times sine of beta or sine of alpha times cosine of beta. But because we now know that we can convert any sine function into a cosine function, I'm not going to worry about those because we can always make them agree with this one particular identity. And it's the one that we are going to use over and over again. So I feel like confusing you guys with a bunch of extra identities will be pointless. And then another identity, and this guy is crazy important. Without this next identity, the field of electrical engineering pretty much wouldn't exist because the math would be too damn hard to do anything. We have cosine x plus j, actually, no. I don't want to do x. I'll make this more explicit. Cosine omega phase angle phi plus j sine omega t plus some phase angle phi is equal to e to the j omega t plus phase angle phi. So this last one is what's called Euler's identity. Named after, he was a German, I believe he was a German, might have been Austrian mathematician that wound up living in Russia for the overwhelming majority of his life. He made a astronomically huge contribution to the field of mathematics and electrical engineering, and effectively lived his life practically penniless because he was supported by the communist Russian government. All this kind of stuff. So in my opinion, one of the most criminally underrated mathematicians and engineers in history, okay? This particular identity is so important because it relates our sinusoidal functions to complex numbers. And that's really all that we're going to be doing for the next 3 weeks until this quarter ends, okay? So there's a couple of other topics with regards to sinusoids that I want to talk about today, but I would like to kind of skip ahead a little bit and work an example problem that will show you how integral understanding some of these identities will be. So in order to work this first example, I need to preface it with a separate example, which is always good news for you guys. So let's say that I have the following circuit. I have a 2 amp current source, which I'm going to call IS. I have 5 ohm resistor, and I have a 2 Henry inductor. And what I want to know is what voltage drop occurs over my voltage source. So how would I approach analyzing this particular circuit? Anybody have any thoughts? And this is, to be clear, this is a DC circuit. So this is hopefully something that we have beaten to death by this point.
You apply KVL around a single loop.
Okay, that's a fantastic idea. So I'm going to call this voltage drop VR and this voltage drop VL. Can anybody tell me what VR would be?
VS minus VL.
So you're not wrong, but I have enough information to get a numerical answer for VR. That's what I'm looking for.
10 volts.
10 volts.
10 volts, right? 2 amps times 5 ohms would give us 10 volts. You're absolutely correct. B. So, as a potential very mini review of one of the topics that you guys might be asked on, those of you that are taking your test later today, in a DC circuit, what does an inductor behave like?
A short.
Short circuit, okay. What is the voltage drop over a short circuit?
0.
So that means that VL must be 0 volts. So applying Kirchhoff's voltage law, we know that VS is going to be VR plus VL is equal to 10 volts. Okay. So what this simplistic problem here is an example of, or what I'm trying to get it to be an example of, is the concept of a forcing function, okay? So when we have a DC forcing function, like a DC 2 amp source, our response, which could be the voltage drop over our inductor, the voltage drop over our resistor, or in this case, the voltage drop over our source, must also be a DC quantity when this thing is operating at steady state conditions, okay? So if we have a situation like this where there's no switches to cause any transient condition to ever occur, if we put a DC excitation into the system, we will always observe DC responses over every single circuit element. So if I change my circuit very slightly, I have some current IS of T. I have my 5 ohm resistor. And I have my 2 Henry inductor. And I'm trying to figure out what my response, Vs of T, is. I would argue that if Is of T is equal to, let's say, 2 cosine 5t plus 12 degrees amps, my expectation is that Vs of T, the voltage drop over that source, will be of the form Vm cosine 5t plus some phase angle theta b volts. So in our first example, we put a DC current in, we got a DC voltage out. I'm expecting now that when I put a sinusoidal voltage in, I will get a sinusoidal voltage out that is operating at the exact same frequency. Does anybody not understand that? All right, so if we wanted to analyze this circuit, we could go about it in pretty much the exact same way, right? I could say that now there's going to be some voltage drop VR of T across my resistor and some voltage drop VL of T across my inductor, where I know that Vs of T will be equal to VR of T plus VL of T. So as an aside here, I could calculate VR of T, still using Ohm's law, right? It would just be R times the current flowing through the resistor, which would give me 5 ohms times 2 cosine 5t plus 12 degrees amps, or 10 cosine 5t plus 12 degrees volts. Anybody have any problem with that?
No.
All right. And I could say that VL of T is L times DIS by dt. So that would be 2 henries times the derivative with respect to time of 2 cosine 5t plus 12 degrees amps. So when I do my derivative here, 2 Henry is going to be there. So the derivative of cosine is going to be negative sine. So I'm going to put here negative 2 sine 5t plus 12 degrees amps. But because of the chain rule, I also have to take the derivative of the argument of the cosine function, which is going to be 5 radians per second, right? So effectively what I'm saying is the derivative of cosine omega t plus theta v is equal to negative omega sine omega t plus theta v, right? Since theta v, our phase angle, is a constant, when we take the derivative of the argument here, the only thing that comes out is the omega. Is everybody okay with that level of calculus?
Yes.
All right. So when I multiply all of these numbers together, I have 2 times negative 2 times 5, so that's going to be 20, or negative 20. So I will have negative, gosh, what just happened there? Negative 20 sine 5t plus 12 degrees volts. So I'm going to give myself a little bit of room here to manipulate things. But right now, we could see that our source voltage Vs of t is then 10 cosine 5t plus 12 degrees minus 20 sine 5t plus 12 degrees volts. So we have a little bit of a problem here. When we look at what our expectation is, we expect our response to be a sinusoidal function having some amplitude Vm, some angular frequency 5, and some phase angle theta v. And our math to this point has led us to a place where we have something similar, but instead of being a single sinusoidal function, it's now a sum of sinusoidal functions. We can use the trig identities that I introduced previously to simplify this guy into and combine it into a single sinusoid. Okay, so we're going to spend the next, as it turns out, several minutes doing just that. So using trig identity number 6. I'm teaching a class right now. Sorry, somebody was knocking on my door very loudly. So using trig identity number 6, I can express cosine of 5t plus 12 degrees as cosine of 5t multiplied by the cosine of 12 degrees minus the sine of 5t times the sine of 12 degrees. And then I'm going to have minus 20. And now I will use trig identity number 5. So I can say that sine of 5t plus 12 degrees is sine of 5t cosine 12 degrees plus cosine of 5t sine 12 degrees. Is everybody following along thus far?
Do you have to memorize these identities?
No, I would, well, okay, so this is kind of jumping the shark here, as it were, although I don't know how many of you guys get that super old Happy Days reference. We are going to find that analyzing circuits in the time domain, like we're doing right now, is going to be incredibly difficult. And so we are going to use an alternative method that will allow us to effectively only have to memorize 1 or 2 of these trig identities at most. For your exam, I have no issue whatsoever if you write down all 10 of those trig identities on an equation sheet, or if I can figure the damn thing out, I will give you all 10 of those trig identities on an equation sheet without any problem. But to be entirely honest, if you rely on using them instead of the alternative method that we'll be developing over the next couple of days, you might get 1 problem on the test finished.
Wow.
Yeah. So
Is the alternative method the Laplace transform?
it is not.
Okay.
That's a fantastic suggestion, and it is definitely related to the Laplace transform, but it is the method that we're going to be dealing with is why you can use the Laplace transform for very complicated circuits effectively, but we're not there just yet.
Okay, thank you.
All right, so what I'm going to do now is I'm going to try to group up like terms here. And so what I mean by that is I can see pretty easily that I have 10 times cosine of 12 degrees minus 20 times sine 12 degrees multiplied by cosine of 5t. And I also have, let's see, I got to make sure I get my signs here right. Let's call it minus for now, but I might change my mind here. So I have 10 sine 12 degrees plus 20 cosine 12 degrees. And all of that will be multiplied by the sine of 5t. So let me just double check here that I got my signs correct. So when I multiply 10 by negative sine 12 degrees, that gives me this guy right here. And I'm multiplying negative 20 times cosine. So I'd have negative 10 minus 20, and I take the negative sign out and distribute it. Okay, I'm correct. So 10 cosine 12 degrees and negative 20 sine 12 degrees, those are just numbers. So we can actually evaluate those guys. So if I do 10 cosine 12 minus 20 sine 12, I get 5.623 cosine, 5t. And then when I do minus 10 sine 12 plus 20 cosine 12, I get negative 21.642 sine 5t. So the math that I have done to this point has gotten rid of our phase angles, right? So we now have the sum of sinusoids where there are no phase angles. So you might be arguing, well, hell, that actually makes things potentially a little bit worse. But I'm going to rewrite trig identity number 6 here in a different color, okay? So we know that cosine, and I'm going to actually, let's write it as a cosine alpha plus beta would be a cosine alpha cosine beta minus a sine alpha sine beta, right? That's just trig identity number 6. Well, I am saying that cosine beta is cosine 5t, and sine beta is sine 5t, which means that this 5.623 we have here represents a actually, I've changed my mind ever so slightly on how I'm going to choose to represent this. Let me erase this crap right here. Instead of potentially confusing you guys with alphas and betas, I'm going to say that Vm cosine omega t plus theta v is going to be Vm cosine theta v cosine omega t minus Vm erase better. There we go. Sine theta v sine omega t. So writing it this way, I can see that this 5.623 represents Vm cosine theta v, and this 21.642 represents Vm sine theta v. Does that make any sense with the equivalency I'm trying to draw between what I have and the trig identity that I'm using? Have I just totally lost you guys?
I was just looking to see where you pulled that trig identity from. Is what I
So
was
that
looking
is,
for.
yeah, trig identity number 6. It's the exact same thing that I had, but I've replaced beta with omega t and alpha with theta v, or vice versa.
Okay, yeah, I got you.
All right. So an interesting thing here, I guess this is another trig identity I could potentially add, but I'm not going to because hopefully you guys are very familiar with it. So let's say that I have Vm cosine theta v, and I square this guy. And then I have Vm sine theta v, and I square this guy. That would give me Vm squared times cosine squared theta v plus sine squared theta v. Anybody not okay with that level of algebra?
And could you take that cosine squared and sine squared and just say it's equal to 1?
That is exactly correct. That would be the next step. So since we know that this is equal to 1, I would just have Vm squared. So to determine Vm, that would obviously then just be the square root of Vm cosine theta v squared, which in our case is 5.623. And Vm sine theta v squared, which that's negative, that's positive 21.642. And that would give us, let's see, the square root of 5.623 squared plus 21.642 squared is 22.361 volts. So we now know the magnitude of our response. And theta v is going to be so let's see. So right now we have Vm sine theta v. We know that guy. And we know Vm cosine theta v. So I would argue that those Vm's would cancel each other out and give us the tangent of theta v. Is everybody okay with that? The definition of tangent is sine over cosine, right?
Yes.
So it stands to reason then that theta v would be the arctangent of Vm sine theta v divided by Vm cosine theta v, which would simply then be the arctangent of 21.642 volts divided by 5.623 volts. Or syntax error, sorry. 75.435 degrees. So we could say that Vs of t is now Vm, or 22.361 cosine 5t plus 75.435 degrees volts. So I would actually like you guys to verify that and see that the answer is going to be pretty close to 0. So just to be clear, a little while ago, we had this was, let me copy it just to be lazy. So these relationships are true for all points in time. So I would argue that if you evaluated these functions at t is equal to 0, so that effectively the 5t portion goes away, I'd like you to use your calculator, make sure to put it in degree mode, and see if 22.361 cosine 75.435 is roughly equal to 10 cosine 12 minus 20 sine 12. So when I do that, I see that there is a difference of 0.0000611199 between the two of them, which that'd be, 6/10,000 off. Seems pretty reasonable to me to be some rounding error that was introduced. So the analysis for this relatively trivial circuit took us a heck of a long time, I would argue. You guys agree with that sentiment?
Yeah.
Pretty dang involved as well. Included the use of several trig identities and kind of going back and forth and all that kind of stuff. So let me copy our voltage, resistor voltage and inductor voltage bit again here. I'm going to introduce a shortcut, and we're going to spend pretty much all of class on Thursday talking about why that shortcut works. And then a couple of other things. Okay. So I'm going to leave my resistor voltage completely alone. There's nothing wrong with it whatsoever. And now what I'm about to do is slightly manipulate my inductor voltage. Okay. So I could say that -20 sine 5t plus 12 degrees is going to look like +20 sine 5t plus 102 degrees. No, that's not right. 192 degrees, because I need to add 180 to it. And then I could say that 20 cosine 5t plus 102 degrees is equivalent so that was using trig identity number 3, I believe, to convert my negative sine function, or excuse me, trig identity number 4 to convert my negative sine function into a positive sine function. And then trig identity number 2 to convert my sine function into a cosine function. So my voltage waveform is characterized by an amplitude and a phase angle in both cases, right? They also have a frequency, but that frequency is the exact same thing. So what I want you guys to do is add together angle 12 degrees as a complex number plus 20 angle 102 degrees as a complex number.
I get the same thing we had in the last question, the last part of 22.36 and 75.434.
22, my pen thing will write, 0.36 with an angle of 75.43.
Yeah.
that number has the same magnitude and the same phase angle as the results of all of that terrible trig and calculus that we spent the better part of probably 40 minutes doing. That is not a coincidence. Okay. What I have done here is effectively represented my voltages that I have by what's called a phasor equivalent representation. I'm going to go into much more detail about what that phasor equivalent representation is. But we can see that if we can look at our time domain functions as complex numbers, we can vastly simplify the amount of calculation steps needed to get the exact same answers, right? So doing it this way up here took several pages of math, the application of some calculus, multiple trig identities. This way right here took a little bit of calculus, or actually I guess the exact same amount of calculus, but overwhelmingly skipped a lot of that trig identity manipulation to wind up with the same result where we have the exact same magnitude and the exact same phase angle. I will more formally describe this process on Thursday. But your homework 19, you can use this complex number representation as simple as we've just done it here to greatly simplify some of the math that's being asked of you to do. Like I would argue that doing it by hand is punishment. Using complex number relationships makes it much, much more easy. And you'll understand why by the end of Thursday's lecture. All right, so I wanted to show you guys why we're going to use complex numbers, because I've been asked numerous times going through this kind of stuff. Oh, well, all this stuff is sines and cosines and this, that, and the other. Why did we bother learning anything about complex numbers? As we found out, it can make the math much, much more simple. So yeah. All right, so the last topic I believe that I would like to talk about today would be comparing sinusoids. All right, so in order to compare sinusoids, 3 criteria must be met. The first criteria is that all functions must be expressed exclusively as sine or cosines. So that means if I want to compare, so let's say that I had dA of t was equal to 10 cosine 8t plus 12 degrees, and VB of t was 9 cosine 8t minus 15 degrees. In order to make a comparison between these two, I would need to either convert the cosine function to a sine function, or convert the, sorry, this should have been sine. The sine to a cosine, right? They have to be matched. So we have a cosine function and a cosine function, so that would now work. Our second criterion is that all of our functions must be expressed positive amplitudes. So if I had the C of t was -12 cosine 8t plus 81 degrees, and Vd of t was 4 cosine 8t minus 60 degrees, I would have to convert this guy to be 12 cosine 8t minus, let's see, 81 minus 180 is negative 99. And now they both have positive amplitudes, and I can make that comparison. Right, and these are just using the trig identities that we've talked about previously. My third criterion is that all functions must have the same frequency. And unfortunately, there is no correction for us to be able to do in this case. So if we had 5 sine 3t and 8 cosine 7t, we could not compare them in any way, shape, or form because they are not operating at the same frequency. So the comparison that we will be making as electrical engineers will usually be what's called determining whether or not a signal is leading or lagging another signal. So give me just a moment, please. All right, sorry about that. Apparently, for those of you who are going to be taking the exam later today, I need to make a quick correction because the portal isn't open for you guys. I'll do that after class. All right, so leading and lagging. So if we look at two sinusoidal functions, let's say that we have this guy, like so. trying to draw relatively evenly, but I don't know that I'm succeeding. And this guy right here. I tried to draw them in such a way that it looks like they have the same frequency. Let's call the blue curve the x of t and the red curve Vy of t. If we compare the peak values that are closest to each other, we can see that the red curve has its peak earlier in time than the blue curve, right? It happens for a lower value of t. So what we would say is that Vy of t leads Vx of t. This is because its peak value occurs earlier, or alternatively, we could say, dang it, it's going to give me that dumb error again. Save, closed, and reopen. Vx of t lags Vy of t because the peak value of Vx occurs at a later point in time than Vy. Now, it is possible to quantify how much Vy of t leads Vx of t, or transversely, how much Vx of t lags Vy of t from a sinusoidal graph like this. But I find that methodology to be incredibly difficult, okay? What I prefer to do instead is what's called looking at a phase diagram. So let's say that I have some signal Va of t that is 10 cosine 12t plus 30 degrees volts, and a signal Vb of t that is 8 cosine 12t minus 45 degrees volts. I'm choosing those angles because I can draw them reasonably well. On a phase diagram plot, like so, horizontal axis, or the positive horizontal axis, is for 0 degrees. Then we would have 90 degrees up here, plus or minus 180 degrees over here, and negative 90 degrees here. So VA, I would represent as a vector that is 10 units long and forms an angle of 30 degrees with the positive horizontal axis. So something like this, where this angle is 30 degrees. And VB, actually, would be a vector that is 8 units long with an angle of negative 45 degrees. So if we wanted to figure out by what angle does VA lead VB, what we would do is we would start at VB and measure the angle between VB and VA. So if we go this way, we have leading. So we could easily see that it takes 45 degrees for us to get up to the horizontal axis, and then another 30 degrees to reach VA. So the angle that VA leads VB is 45 plus 30 is 75 degrees. If instead we wanted to know by what angle does VA T lag VB of T, we would instead measure in the other direction. So it would take us 45 degrees to reach here, another 90 degrees to get here, another 90 degrees to get here, and then 60 degrees until we actually reach our vector VA. So that's 180 plus 60 would be 240. So it looks like 285 degrees. And there we have it. So when we're measuring leading and lagging, we always start with the second waveform as our reference point. And if we want to know by how much it leads, excuse me, we go in a counterclockwise direction because we're effectively saying how much more positive is the phase angle than the reference VB in this case. And when we do lagging, we're effectively saying how much more negative is the phase angle than my reference. So I want to do another quick example where you guys try to answer the questions to see if you're catching anything at all here. So let's say that I have an angle of 110 degrees for Vx and an angle of 70 degrees, or that probably actually looks closer to 60, so I'll just put 60 for Vy of t. How would you go about figuring that out?
I'd start at Vx and go clockwise, no, counterclockwise.
Counterclockwise, right? So we'd start here and go all the way around, right? So that would look like, so if this is 110, then this guy right here must be 70, then 90, then 90, and then another 60, right? So 70 plus 90 plus 90 plus 60, 180 plus 60, 310 degrees, I think is total. Does that sound about right? 130 plus 180, 310. Yeah. So the process is literally that simple. Now, I'm going to give you fair warning. This is another hiccup with web work. Web work, like the way that we're doing this, the answer to this question is 310 degrees. You could alternatively say that it's negative 50 degrees because we understand that negative 50 degrees and positive 310 degrees represent the exact same angle. Web work does not understand that. So if you follow the methodology that I have given you here, and you find that web work is not accepting your answer, all that you need to do is add 360 degrees and check that answer, or subtract 360 degrees from your original answer and check that one. It will be one of those. So effectively, again, all I'm saying is that web work does not understand that negative 360 degrees is equal to 0 degrees, is equal to positive 360 degrees, is equal to 720 degrees, et cetera, et cetera, et cetera. So just add or subtract 360 degrees from whatever answer you get if web work doesn't take the one you initially get as being correct. And I'm trying to figure out a way to make web work accept these things, but I haven't figured it out yet. So anyway. All right, so I think that's enough out of me because I'd like for you guys who are about to take your test to have a little bit of a break to, go use the restroom, maybe grab a bite to eat, kind of reset before you go back to revisit a completely different topic. But before I get out of here, does anybody have any questions on the stuff that we've covered today? All right, so on Thursday, we will get into what's called frequency domain circuit analysis, a means by which we use complex numbers to avoid using trig like the plague. Effectively, that's the best way that I can explain it. So I will see you guys on Thursday to get deep into frequency domain analysis. Good luck on your exam for those of you that are about to take it.